Good. Okay, well, what we'll cover tonight is there's one aspect of computer arithmetic that I still want to talk about, and that's multiplication. We also need to do the course evaluations. And then everything else is just final exam tutorial. Okay, so let's get started with the topic of multiplication. Typically, when people think in terms of how computers, I'll try to stay a little bit more in the center here. As long as that isn't a camera that makes me look fat. So, you know, I have now beaten my son's challenge. I just need to go and hit that, maintain that for July 1st and the next 24 weigh-ins. But anyways, so still have a ways to go. I'm still moving it.
Big milestone.
What's that?
Big milestone.
Well, thank you. Yes, I felt pretty good about that. So now we'll see how good I feel when I'm running 13.1 miles in a few weeks. So, but I survived 10 miles last Saturday, and it'll be 11 on this Saturday. And
so you're going to do Boston Marathon next year?
Let's not push it. So, I'm an old man. So, but anyways, back to multiplication. If most people, when they start thinking about how a computer does multiplication, they oftentimes tend to think in terms of, well, when I was in grammar school, I had to learn times tables, so computers must be good at times tables, and quickly they go from there. Well, again, the thing about computers is everything is done in binary. And so actually the binary times tables are incredibly simple. 0 times 0 is 0, 0 times 1 is 0, 1 times 1 is 1. Not too tough to go and remember those. So if we were to look at a number like, let's say, we'll just do a 4-bit multiply just to keep it kind of reasonably straightforward. So if we were to do a binary multiply like this, it all works the same way. And by the way, just so I can talk without saying top number and bottom number, the top number is the multiplicand, the bottom number is the multiplier, and the end result is the product. So if we just do it in terms of the same way we learned to do, maybe this generation, the way you learn to do it is you just enter it on the calculator. But in terms of just being able to do multiplication the old-fashioned way, well, we just go and take the multiplicand, and we first do it times the least significant digit in the multiplier. So 1101 times 1 is 1101. And then we go to the next bit in the multiplier, 1101 times 1, so shifting over the result by 1, 1101 here. And then 1101 times 0, well, that's pretty easy. And then 1101 times 1, and then we just add it all up together. And here's our result. And so there shouldn't be any, great mystery about how binary multiplication works. The only thing that does need to be done a little bit differently for computers is this is how a human being would do binary multiplication. The thing about this that might not look that bad right now is that if we went and made this a 32-bit multiply, then we'd wind up having an issue because we have 32 of these partial answers, and then after we accumulate all those 32 partial answers, we then have to add them all up together. And from a computer standpoint, that's far from optimal. It would have to find some place to put those 32 partial results and then add them up in some kind of an efficient way. So if we were to make this more computer-oriented, more the way in which a computer is going to do this, well, what's going to happen is that as soon as we have any two partial results, we're going to add those two partial results together. Okay? So let's just do this again. 1101 times 1011. once again, yeah, we'll look at the least significant bit in the multiplier, so 1101. Then we'll look at the next bit in the multiplier, 1101. And at this point, we're going to add the two partial results together. We never allow ourselves to get more than two partial results. We have hardware that can add two partial results together quite easily. We don't want to have to go and have hardware that takes 32 partial results and efficiently handles that. So let's take that. Just make sure I do that right. Yeah. So this is our partial result. So this was as a result of bit 0 in the multiplier. This is bit 1. And this is just the combination of those two. So now we look at bit 2 in the multiplier. We'll multiply that times 0, so we don't need to add that in. And then times bit 3 in the multiplier, 1101 times 1. We just need to line it up in the correct place. So it'll be 1011. So we're going to get 1110. And we'll get the correct result, but this is the more computer-oriented way in which we would do this. That is, as soon as we have two partial values, we'll just add them together. Okay? Any questions on that? Okay, let me just take it one step further, and we'll do the same problem. The only thing is that we'll just, we'll make kind of internal registers about all of this. So we'll have a multiplican register, we'll have a multiplier register. This is still going to be on screen?
Yes.
Okay.
It's still.
We're going to have, I was going to call it an ALU, but really it's just an adder. And then a product register. So, if we start out our product register, we'll initialize that to 0. We can put our multiplier here in our multiplier register, 1011, and our multiplican we'll put up here, 1101. Now, in terms of the size of these registers, this register in our 4-bit example, this is actually going to need to be an 8-bit register. And in a 32-bit multiply, this would actually, in the real world, this would have to be 64 bits wide for reasons that I'll point out shortly. The multiplier register, that's going to be a 4-bit register in our kind of scaled down world. It would be a 32-bit register in the 32-bit world, and our product register is going to be a 64-bit register. Because if we're multiplying two 32-bit numbers by each other, we're not necessarily going to be able to fit the result in a 32-bit register. So if we just start this out like with this initialization, and what we will be doing is based on the least significant bit in the multiplier, we will determine whether we're going to be adding in the multiplican to our running product, much like we just do right here. So our running product, we're going to accumulate that running product, and we'll go from there. Our basic workflow is going to be that we will essentially say say that if the least significant bit in the multiplier is equal to 1, then we'll just go and take whatever's in the product register and we'll add to it whatever's in the multiplication. Okay? And regardless of whether that's true or not, we'll go and shift the multiplier register to the right by 1 bit, and we'll shift the multiplicand register to the left by 1 bit. Okay, oh, and I should have put that on this. Well, anyway, we'll be fine. So let's just look and see how this all works out. So we've initialized our registers. Now let's just go and follow this, this approach and say, okay, let's look at the least significant bit in the multiplier, and if that is 1, then let's perform that addition. Well, this is a pretty easy one, in that our least significant bit in the multiplier is a 1, so we're just going to add what's in the multiplicand to what's in the product register. Well, 1101 plus 0 gives us 1101. Now we're going to shift the multiply register to the right by 1 bit, because it's a whole lot easier for a computer to take the approach that now that I've finished handling this bit, I'm going to get rid of it. And I'm just always going to look at the least significant bit in that register. That's a whole lot easier than what we were doing before, in that we were saying, okay, well, I'm going to handle this bit, now this bit, now this bit, now this bit. Well, it's a whole lot easier for a computer just to go and say, okay, I'm done with this bit in the multiplier, I'm shifting it to the right, I don't need that bit anymore, okay? Now, why are we shifting the multiplicand to the right, to the left by 1 bit? We're doing that so that each time through this loop, and we're going to go through this loop however many bits there are in the multiplier, so that each time we're going to wind up adding in the multiplicand in a shifted over position, just like in the standard way that's comparable to grammar school decimal multiplication. So we've done our shifting. We've handled the first bit in our multiply. Now let's look at the next bit in the multiply. Well, we still follow the same algorithm. We go and say, okay, the least significant bit in the multiplier is a 1, so we're going to go and add the product register to let me just take a look and see how I want to show this. Yeah, so we're going to take the product register, 1101, and we're going to add it to the multiplicand register, 11010. And so when we add this together, we'll get 1, 1, 1, 1 plus 1, 0, carry of the 1, 0, carry of the 1. So we'll get 10011, and that is going to be the new value that we're going to put into the product register. Now, before I put that in there, let me just point something out. This is, again, comparable to what we did over here. We've got the 1101, and we're adding, well, there's an implied 0 here. So we're adding 1101 plus our multiplicand register, and we're getting this partial result. And so that's going into our product register. So we can put that new value into the product register. And now we're done with bits 0 and bits 1. Now with bits 2, bit 2 in the multiplier, oh, we need to do the shifting. So we'll shift the multiplier register to the right by 1 bit, and the multiplicand register to the left by 1 bit. Okay, now we go through this our third time. We're going to go through the loop 4 times because we've got a 4-bit multiplier. Now we look and we say, okay, well, my least significant bit in the multiplier is not 1, so I'm not going to add anything. I'm not going to update the product. I'm just going to go and shift the values in the 2 registers. So I'm going to shift the multiplier to the right by 1. Okay, let me just rewrite it so it's all the way over to the right. And I'm going to shift the multiplicand to the left by 1. So that's all I have to do for that particular bit. Now I go and I do this loop one last time, and I look and see, okay, my multiplier is a 1, so I'm going to add what's in the product register, which is 100111, and add to it what's in the multiplicand register, which is 0, 0, 0, 1, 0, 1, 1. And on audio, I'm going from the least significant bits there. So now when we add it together, we'll get 1, 1, 1, 1, 0. 1 plus 1 is a 1, 0. Put down the 0 here. Carry the 1. 1 plus 1 is 1, 0. Put down the 0, carry the 1. And we got the correct result, which is what we would have expected. Again, just to compare it to what we had over here, the 10011, that's what's in our product register before we start this whole operation. When we put in the implied zeros, well, this is what's in the multiplicand register. So it's all what we were doing before, but this goes and shows you in a more hardware-oriented way how multiplication would get done. Okay? Any questions on this?
Not in the exam.
Yeah, so those are,
Leave only relevant.
not to be totally practical about it, but yes, I did say last week that this last topic, I would not include this on the exam because my preference, well, first of all, this is a tough topic to put on the exam and not just make a matter of memorization. But also, I have a very, very strong preference for not including on any exam what has just been covered and you haven't had a chance to kind of assimilate it. So yes, from a practical standpoint, now please nobody go and just tear that sheet out of their notebook and just rip it up. Question?
Yeah, so like if we were back in the day, for like the state-of-the-art thing, we were building computers out of,
Yep.
and we had we, for whatever reason, decided to have like a multiplication instruction.
Yep.
Would that be implemented as a really expensive one cycle assembly instruction or a 32 cycle instruction?
It kind of depends. It can be done in different ways. It can be done as, now, let me just back up and point out that in the, I know the timings of some of the original Intel architectures, which was, if you had a simple instruction, it might take 2 or 3 cycles. These are not pipeline machines. 2 or 3 cycles, but a multiplier divide would take like about 100 cycles because it's just, there's a lot that has to get done there, even in, pretty advanced hardware. And let me just point out that the book does go and take this approach and then adds 2 optimizations to it. Most of the optimization is scaling back on the hardware, but it makes it like 100 times less intuitive. So I don't cover it because I want you to just get the intuitive idea of how to do multiplication and kind of demystify how the whole thing works and just realize that there are certainly optimizations to it. Now, there are some optimizations based on the fact that if you have certain multipliers that have strings of 1s in them, and this is very prevalent in negative numbers, but if you've got a multiplier, let's say you're multiplying something times 0, 0, 1, 1, put a few zeros. If you're multiplying a number by that multiplier, well, you'd have to be adding in the value a whole bunch of times. Well, there's an optimization called Booth's algorithm that would go and say, well, let's translate this into 1, 0, 0, 0, 0, 0, 0, 0, 0. So we only have to go and add in the multiplicand once, and then we just subtract it once just to go and make it so it all works out. In fact, since you asked that question, let me just point out that when my daughter, who is now full grown, but when she was like 7 or 8, she was this precocious little kid who she got a calculator and she figured, okay, well, let's see how smart Dad is, which is always a scary thing. And she said, okay, well, what's 99 times 99? For a 7-year-old, that seemed like a tough question. Well,
It's the highest I can count.
well, no, it just seemed like, well, I don't think my dad's too smart. Let me give him something that'll be tough, but not too tough. But I was able to do the same thing. I just said, okay, I'm going to change my multiplier to 100, I'll just put 2 zeros at the end and subtract out ones. And I gave her the answer. She checked it out on the calculator. I was like, wow, Dad isn't as dumb as I thought he was. And then she said, okay, well, let's do 999 times 999. And I did the same kind of trick, and she was really impressed. Then she said, okay, what's 52,300? You know, she gave me something I couldn't do the trick on. And, you know, some of that illusion was gone. And in a few years, she was a teenager, and then she knew I was an idiot. But that's how it is with teenagers. But in any case, there are different optimizations that can be taken in real hardware. However, having said that, there's two different approaches to doing multiplication in real hardware. You can go and you can actually build in a multiply instruction into the instruction set. And then that instruction oftentimes doesn't fit very well into a pipeline, and it's oftentimes done kind of off on the side in its own multiplication unit. Or what some architectures choose to do is they do what you can kind of consider to be like a mini multiply. Kind of sounding Austin Powers there, but a mini multiply where you would do 32 of these mini multiplies, and that way it would fit totally into the whole pipeline approach. So there's different ways of attacking it, and you know, a lot depends on just how things fit into the rest of the particular architecture that you're talking about. So that was a pretty straightforward question, and I took about 10 minutes to answer it, but you know, hopefully that was of interest. Anything else on this? Okay, so if you're interested, again, the book does show the two optimizations. The book also gets into division. Well, division is just kind of a little bit of a messier, backwards version of multiplication. And I'm not going to go and cover that either, because I think once you've kind of had the whole binary multiplication demystified, I think you can kind of visualize the same kind of thing happening in a little backwards fashion with division. So that's not going to be a topic that we'll cover, but you can certainly check that out in the textbook. Okay. So any other questions? Okay. Well then, actually, let's take now to do the. How many? I sent out an email about this. How many brought in a smart device that they can go and take the eval on? Okay, so let me read. I'll read the directions, but then I need to leave the room. So